Imagine you're holding a freshly machined solid metal block. You take your precision calipers, you measure the height, you check the width, you check the length, everything is dead on. It's perfectly within the specified plus or minus size tolerances on the blueprint. So you confidently send it down to the assembly line, but when they try to actually mate it with another component, it completely fails to fit. Or, maybe it's a cylindrical pipe that measures perfectly, but when you install it, it utterly fails to seal and just leaks fluid everywhere. How is that even possible? How can a part measure perfectly, yet fail completely? Well, welcome to Lesson 3 of our GD&T Explainer Masterclass, where we're going to solve that exact mystery. To really understand this manufacturing mystery, let's look at a comparison. On one side, we have a perfectly flat, pristine, rectangular block. On the other side, we have an exaggeratedly warped, wavy, almost potato-shaped block. But here is the massive pattern interrupt. Both of these blocks can technically pass the exact same plus and minus size limits. No way, right? But it's true. And that's because basic size limits just check the local distance between two opposing points. You can take a micrometer to the valleys and peaks of that wavy block, and as long as that local distance is within tolerance, it technically passes size inspection. So size limits alone absolutely do not perfectly control a part's overall shape. So, I gotta ask you, which one of these actually works in a real-world assembly? Obviously the flat one, for sure. But if a basic set of calipers or micrometers can't tell the difference between a perfectly flat surface and a wavy potato, how do we catch that defective part before it ruins an entire engine block or a critical aerospace build? Well, to catch that wavy part, we need a highly specialized set of rules. We need form tolerances. Okay, let's dive into this. Looking directly at the ASME Y14.5 standard for the 14 geometric characteristic symbols, I want to draw your attention right to the top category, form. You've got straightness, flatness, circularity, and cylindricity. But the single most important rule of this entire category is sitting right there in the far right column. Look at the datum reference required section. It says no all the way down. Form tolerances never use datums. So, what does no datums actually mean in everyday engineering practice? It means that these four symbols are entirely self-referencing. As the ASME standard defines it, we're controlling a geometric feature strictly relative to itself, completely independent of any other feature or datum reference frame. We aren't orienting it to the bottom of the part, we aren't locating it from a hole, we're not squaring it to a sidewall, nothing like that. And, this dramatically simplifies things for us. We're purely evaluating the independent shape of this one specific feature. Is it straight? Is it flat? Is it round? That is literally all we care about right now. Before we look at the individual symbols, let's set up a quick mental model. We can map all four of our form symbols across a super simple 2D to 3D logic board. For the columns, we have the type of geometry, straight and flat features versus rounded features. And for the rows, we have dimensionality. Are we looking at a 2D cross-section or are we looking at a full 3D surface? If you can remember this grid, it's like a giant puzzle. You can pattern match the logic of the entire form category. Let's start up in the top left. Number 1. Straightness, 2D line elements. Because straightness is a 2D symbol, we're focusing on evaluating a surface just one single line at a time. The standard dictates that straightness limits the variation of line elements in a single direction. The visual you really need to lock into your brain here is the tolerance zone itself. For straightness, this zone is always bounded by two perfectly parallel lines. Just imagine resting a precision straight edge right on the surface of your part. You're simply verifying that the single line profile of that surface doesn't dip, bow, or wave outside of the tiny gap between those two parallel lines. Oh, and as a really important side note, the standard also specifies that if you attach the straightness symbol to a size dimension of a cylinder, it can uniquely apply to what's called a derived median line, which is essentially the abstract imperfect center line of the feature. But for basic surface straightness, just remember, one line bounded by two parallel lines. Number 2. Flatness 3D surface control. Let's move to and see how this builds from the top left of our matrix down to the bottom left. We're upgrading from evaluating a 2D line to an entire 3D surface. Flatness simply takes that 2D straightness concept and sweeps it across a full area. The standard tells us that flatness requires all points of a surface to lie within a tolerance zone bounded by two parallel planes. So, instead of two parallel lines, imagine trapping your entire part's surface between two perfectly flat parallel sheets of glass. If any point on that entire surface bows up or warps down enough to break through the glass, the part is scrapped. The standard even notes that flatness can be applied on a unit basis. That means you can specify that a surface must remain extremely flat within a small specific area, say like a 25 by 25 millimeter square, which limits those abrupt surface variations across a much larger plate. Number 3. Circularity 2D cross-sections. Now, let's switch gears from flat geometry over to round parts, moving to the top right of our mental matrix. The rule for circularity, which is sometimes called roundness, is that each cross-section of a surface must independently lie between two concentric circles. Now, what's really interesting about this is that word, independently, because we're in the 2D row of our matrix, we're evaluating the cylinder slice by slice, literally just like a loaf of bread. The standard dictates that this applies independently at any plane. That means each individual slice can actually have a slightly different center point, as long as the surface of that specific slice is perfectly sandwiched between its own two concentric circles. So it definitely catches if a slice is oval-shaped or egg-shaped, but it doesn't care at all how those slices stack up against each other. So time for a quick quiz to test your new GD&T X-ray vision. Imagine a cylindrical pin. You check the circularity of 50 different slices, and every single slice perfectly passes 2D circularity. It's round at every single cross-section. But when you look at the pin from the side, it bulges in the middle like a barrel, or maybe it pinches in the middle, becoming what we call wasted. The standard specifically warns that full straightness might not be available in cases of wasting or barreling. So if circularity only checks independent 2D slices, what symbol actually catches a part that is wavy end to end? Number 4, cylindricity, 3D round geometry. To catch that barreled or wasted defect, we have to move to the bottom right of our matrix and unleash the absolute boss-level 3D symbol for round geometry. Cylindricity is the one symbol that practically everyone underestimates, but manufacturers respected deeply because it's a strict, all-encompassing control. As the ASME standard explicitly points out, cylindricity is a massive composite control of form that commands three things all at once: the straightness of the cylinder, the circularity of the cylinder, and the taper of the cylinder. It evaluates the entire feature at the exact same time. And this brilliantly illustrates the difference between 2D and 3D geometric controls. Because it's a 3D tolerance, cylindricity creates one single tolerance zone bounded by two perfectly concentric cylinders for the entire surface simultaneously. Unlike our circularity slices where the center points could kind of drift around, cylindricity forces the entire length of the surface into one rigid 3D jacket. It locks both the circular elements and the longitudinal elements together. If your part is barreled, wasted, or tapered, even if it's perfectly round at every individual slice, it will absolutely crash through those two concentric 3D boundary cylinders and fail inspection. So look at how beautifully simple this system is when you really break it down. We have two 2D controls, straightness and circularity, and we have two 3D controls, flatness and cylindricity. We use parallel boundaries for flat things and concentric boundaries for round things. And the core takeaway that ties all of this together is this direct quote from our reference documents. Form tolerances never reference a datum, they control a feature relative to itself. We have officially mastered how to evaluate independent features without needing a single external reference point. But I want to leave you with a bit of a provocative thought here. Let's say you've manufactured a pin with absolutely perfect cylindricity and a block with absolutely perfect flatness. That's great, but how do you ensure that perfectly cylindrical pin is located in the exact right spot on that perfectly flat block, right? How do we relate these perfect shapes to each other to build a machine that actually functions? Well, that requires exactly what we completely ignored today. So the crucial point is we need datums. Orientation, location, and run-out tolerances all absolutely require a datum reference frame, and that is exactly what we are going to build from the ground up in Lesson 4. I'll see you there.